Day 15. 1 minute to go. About to start. And I'm out of coffee. I need to get some more coffee next time I go out. So I'm gonna have to solve this one, coffee less. uh Here we go. Beacon exclusion zone. You feel the ground rumble again as the distress signal leads you to a large network of subterranean tunnels. Also, we've gone into this cave. Okay. You don't have time to search them all, but you don't need to. Your pack contains a set of deployable sensors that you imagine were originally built to locate lost elves. The sensors aren't very powerful, but that's okay. Your handheld device indicates that you're close enough to the source. This handheld device does everything, doesn't it? To the source of the distress signal to use them. You pull the emergency sensor system out of your pack, hit the big button on top, and the sensors zoom off down the tunnels. Oh, so these are like flying sensors. Once the sensor finds a spot it thinks it will give it a good reading, it attaches itself to a hard surface and begins monitoring for the nearest signal source beacon. Sensors and beacons always exist at integer coordinates. Each sensor knows its position and can determine the position of a beacon precisely. However, sensors can only lock onto the one beacon closest to the sensor as measured by Manhattan distance. There's never a tie where two beacons are the same distance for sensor. It doesn't take long for the sensors to report back their positions and closest beacons. So we get sensors and they say where the closest beacon is by the Manhattan metric. Cool. Each sensor only identifies its closest beacon. Hello, DJ. So this is like... what's it called? Well, let's keep reading first. The census club. Okay, so that's the sphere under the Manhattan metric, essentially, or a disk. So if we see a beacon there, then we know that all these spaces can no longer have beacons. I'm guessing we're going to end up finding the union of disks, for which there are algorithms. There are algorithms for doing that, but they're complicated. But I'm guessing we can just do it with a giant for loop, and it should be okay. We're triangulating, kind of the opposite. Basically, the sensor tells us where the nearest beacon is, and well, actually I don't know exactly what the objective is here. I need to keep reading. So we want to count the positions where a beacon cannot exist. Wait, just a single row? Wait, what do you mean by that? So suppose you have an arrangement of beacons and sensors, like an example above, and just in the row where y equals 10, you'd like to count the number of positions a beacon cannot possibly exist. The coverage from all sensors near that row looks like this. Okay. There are 26 positions where a beacon cannot be present. Okay. So it's sort of like figure out where it is by figuring out where it isn't. Reminds me of that great fake Navy training video about how a missile guidance system works. I haven't seen that. But yeah, I guess it's the same principle. We just have to keep ruling out. Alright, well, so what does the input look like? Oh, that's it. Ah, so he's gone for big coordinates this time. And, oh, is that the video? Okay, I'll watch it after the stream. So he's trying to catch out people who do what we did for the last problem, which was to just create a grid of coordinates starting from 0. But this is too big, clearly. So we need a hash map instead. By the way, speaking of the guy, he actually showed up in my stream yesterday. I don't know if you were there at the time, DJ. The guy who made this site, he turned up at the end of my stream. Eric Wastel. So I guess he must be watching lots of people at the time of release of the problem because he's interested to see how they tackle it. Alright, so let's take this input. So basically everywhere in the universe, in the infinite range, is a possible beacon spot. And each time we see one of these, we can rule out beacons. Now, let's have a look at this. So closest beacon is at 4 million. So we can't just go through a million different spots and rule them out. And it's actually more because it's like basically a rectangle. So we need to be smarter about this. So what we only want a given row. How many positions cannot contain a beacon? All right. So we need to restrict ourselves to okay. So we're basically, it's projection. We want to take each of these disks and project it onto that row. So we don't actually deal with the rest of the disk, just what it looks like against that row, essentially. Alright, let's do some coding. Well, okay. Now I could just pause this and look for the comma and yeah, we'll do that. But I could actually just edit this, edit out the sensor. Actually, that's not hard to do. If I use Control F, sensor at x equal, and just replace with Where's replace with? What happened to... What happened to find and replace? Why wouldn't that be... What? What program is this? This is PyCharm. Okay, why would they move that somewhere else? There used to be a find and replace. Select occurrence. Let's see. Edit. Find. Replace. Wait, what? Why is that blanked out? Okay, Control R brings it up. Replace with empty space. Yeah, let's do that. There we go. Let's say closest beacon is at X equals. Replace that with a comma. Alright, that looks good. Just empty spaces, get rid of those. We don't want the Y equals, we can deal with that. Y equals. There we go. Good old find and replace. So it's sensor X, sensor Y, beacon X, beacon Y equals int Z for Z in line dot split. Run that, make sure it parses correctly, and it doesn't because we have to split on comma. Okay. All right. Row is Y equals 2 million. Okay. Hang on. Yeah, okay. So let's call this scan row equals 2 million. So for each, so basically we want to keep a set of non-beacons spaces where we've determined absolutely cannot contain a beacon. Is there any beacon in the row 2 million? Yeah, there is one. So they did that. There's a couple. They did that to catch us out. Because the actual beacon itself isn't part of the disk, because that's actually a beacon. Disk is spaces which are not beacons. Okay, so oh, okay. How do I get started? I have to visualize this. So we have a row which we're interested in. We have some sensor. We have a disk around it of a certain distance. And we want to find the intersection of that disk with the row. Oh! Maybe it's not actually that complicated. So basically, you take... It's Hamming metric, so... Oh, I can't... So you've got your sensor. So let's take a certain number of steps until we're on row 200,000, 2 million or whatever. But keep track of how many steps we took. And once we reach that point, we have a few steps left. We can go left or right on that row. All those spaces we cover are the ones that can't be beacons. So, I don't know if that made any sense. Essentially, we want to find the... First, let's find the distance of this beacon from S, because that tells us the radius of this disk. So, radius equals absolute value of bx minus sx plus absolute value of by minus sy. Okay. So that's how many steps we're allowed to walk in any direction. And any spot we can reach with that many steps, it cannot be a beacon. Except for the one that's actually a beacon. So let's walk onto the scan row. So dist to scan row equals absolute value of scan row minus sy. So if we do that, we've walked onto the scan row. The num steps left equals, that's how many steps we can now take, equals radius minus dist to scan row, which could be negative. It could be that we were just way away from the if num steps left is less than 0, strictly less than 0. If it's 0, that means we at least have 1 point on the row, but nothing else. Then we move on to the next line. So if we're here, that means we have a few steps left over. So we could go left or could go right. So we do for x in range, so we want to start from the left and move to the right. Now this might still take too much processing time, but let's try it anyway. So it might be that we now want to calculate unions of linear intervals, which is another algorithm. But let's just do it this way first. So for x in range, so starting from sx minus num steps left and finishing on sx plus num steps left. We have to say if So the position is X scan row. That's what we're looking at here. If pos is not equal to the beacon, because they were trying to trick us by including the beacon as on that row sometimes, then non-beacons dot add pos, and then we simply print length of non-beacons. I have a feeling this might take too long though. Yeah. Okay. So. Oh, it does finish. Okay. Because basically at this point, what we're doing is we're finding a interval on the line, and we're finding lots of intervals on lines, and you want to take the union of them. But taking the individual points is pretty slow. There's an algorithm which involves sorting by event times or something, which does this faster. But okay, this actually ran. So let's try that. Correct. Alright, short part 2. Your handheld device indicates that the distress signal is coming from a beacon nearby. The distress beacon is not detected by any sensor, but the distress beacon must have X and Y coordinates each no lower than 0 and no larger than 4 million. It's easy in implementation. The tricky bit is visualizing the geometry of this, because Hamming metric gives you some strange shaped disks. I say disk, and that might be misleading because it's not literally a circle, but in mathematics we say disk to mean the set of points that can be reached by traveling a certain distance. But of course we're not using a Euclidean distance, we're using Hamming distance, so the disk ends up looking like a diamond. And there's probably some really smart algorithms for working out intersections and unions of Hamming distance disks that I don't remember. It's like, oh man, this is computational geometry. This was my PhD specialization. I don't remember this stuff. There's this thing called the trapezium map, which you often use, and that's useful for finding. I mean, okay, in America they call it the trapezoidal map. In Europe we call it the trapezium map. Or specifically in British English we call it the trapezium map. Man, I can't believe it has a Thai name. Well, it would. I mean, I'm sure they'd learn it in Thailand as well. But it's like... Alright, I digress. But it's an interesting thing to read about. It's useful for finding intersections of shapes, polygons. Alright, so to isolate the distress beacon signal, you need to determine its tuning frequency, which can be found by multiplying its x coordinate by 4 million and then adding its y coordinate. Okay, fine. So we basically want to find its coordinates, the beacon. In the example above, the search space is smaller. There's only a single position that could have a beacon, x equals 1411. There's only one possible position for the distress beacon. Okay. This is definitely a fundamentally different problem from part 1. We want to find the unique... Okay, so now that we're restricting to 0, 4 million, the square, 4 million either side. We can't just check every element of that square because that is still 4 million by 4 million. That's too big. Okay. Alright, let's have a look at this example. So they said x and y, for the example, they're restricting to 20. So it would be like... up to here, this column, this row. So within there... Oh, but this is not filled out, but lots of these sensors have corresponding beacons. So there's one space left, and they said that's 1411. So there. This, okay, not sure how to get started here. This is hard. It's hard because of the numbers involved. We can't just cross out, like even crossing out beacons on a line took a few seconds. But if we're now doing it in a rectangle, it's just gonna take too long. So we're fine. We have to look at these numbers. There's different things we could do. Let's print these radii. I want to see what they look like. These are the radii. These are big. So square that and you get the size of the rectangle. That's way too big. It could be that the numbers are... Well, how much do they actually intersect with our rectangle? They do, always. In some cases, they seem to be fully contained within our rectangle, or almost. This one, for example. I'm a bit stumped. I mean, one thing we can do is deal with horizontal line segments. I mean, we know how to deal with one row. Okay. Ah, so that's probably what they're getting at here. We know how to deal with a single row. I can't do that 4 million times. But the moment that we've fully covered a row, we can move on to the next row. Oh man. So what I'm thinking is we hello, Bad for Beans. This one's tricky. But there is some special property of this beacon, this unique beacon. If what they say is true and it's the only possible place for the beacon, that means on all 4 sides of it, it must be touching one of these discs. So we only have to look along. We know it must be along the edges of the discs, or one space, just one space further than the edges of the disc. So we don't have to look inside the discs. How do we use that? How many discs are there? Not that many. So for each disc, we could assume that that's the disc which is adjacent to it, and proceed as if it was, and see if we can locate which one it is. Would that work? Hang on, so I'm drawing diagrams, so I'm trying to figure out what it looks like. Either we have a disc which is touching it on a corner, or we have a disc which is touching it along an edge. Alright, come on, let's do something. Let's try what I said. For each disc, we what problem am I working on? This one. Day 15. It's about basically intersections of disks in the plane. Well, not intersections, unions of disks in the plane. Well, discs. I say discs, but really it's diamonds. Discs under the Hamming metric. This part 2 is quite difficult. We have really big discs. And we're trying to find the unique spot which is not covered by any discs. So apparently the discs span the whole of our 4 million by 4 million square, and there's one cell. But the fact that we're told that there's one cell is important information. That means it's on the edges of discs. So my idea is we look along the edges of each of these discs and use those as our candidate squares. So let's say alright, part 2. Alright, let's just put all these discs in a list to begin with. Discs.append. So we want the X position, the Y position, and the radius. That tells us everything. We can print the answer to part 1 and now deal with part 2. So for XY radius in discs, so we're going to pick a disc. We're going to say everything just outside that disc along the edge is a candidate for this beacon. How do we get that? How do we generate that list of cells? I forget how to do this. Trying to generate all the cells of r+1 distance from xy, but it's Hamming metric, so it's diamond shape. Hello, Ku. So let's make a method for this. Define get boundary of a disk with center xy and radius r. So the top is x so the top is xy plus r. Is this inverted? Is y in the downwards direction? Not that it matters. I could still call it top. Alright. So we just want to walk. Okay, so yield top while hang on, not top, say temp equals while temp is not equal to x plus r. So now we want to move to the right, but diagonally. So x plus r y. Temp equals temp 0 plus 1. Temp 1 minus 1. So now we're moving diagonally. Yield temp. So we'll end up yielding the rightmost point. And then do the same going down on the left. So it'd be minus 1, plus 1, yield temp. And then we want to go up and left. Is there a cleaner way of generating this? I don't know. But this one is x y minus r. Then this one is x minus r y. We go minus x plus then the y. And then finally it's always a better way to code something. Just, is it worth the effort? Well, when I say better, I mean the main metric I mean is quicker to type. There probably is something clever you can do to generate the boundary of a diamond. I guess this is not too bad. X, Y, plus R. I think I've generated the top twice. Yeah, we can just take that one out. So I think that will generate the boundary. So I have to check these indices. So we start with the top. So we're going to the right, so it'll be x plus ry. Then we're going to the bottom, which will be x, y minus r. Then we go to the left, x minus r, y, and then x, y plus r. Then the directions, positive x, decreasing y, decreasing x, decreasing y, decreasing x, increasing y, increasing x, increasing y. Seems right. Alright, so candidates equals set. So for pause in for px py in get boundary centered on xy, but just 1 unit wider, so it's just outside the disk. If 0 is less or equal to px is less or equal to 4, 1, 2, 3, 1, 2, 3. And is that it? 4 million? Yeah. I feel like this will run in time, but it might take minutes. Py is less or equal to 4, 1, 2, 3, 1, 2, 3. Candidates dot append Good excuse to get a new laptop, faster process. I don't think it'll make much difference. Like, the thing about these problems is the difference between a good algorithm and a mediocre algorithm and a bad algorithm is massive. It's like, it's either going to take minutes or it's going to take thousands of years. Actually, for some of these problems that hasn't been true. You can actually run it for like several minutes, maybe under an hour, and eventually get the answer. But this one in particular, I can see it taking a ridiculous amount of time. I don't think even on a faster processor you could. These are radius of millions, so square that and you get rectangles of whatever a million times a million is. A trillion? No. Quadrillion? Yeah, no computer could handle that, so... Alright, candidates.append, no, dot add. Alright, let's print the size of these candidates lists. This tells us how many are on the edges of these disks. That'll give us an idea of what we're working with. Hang on, I'm printing too much stuff here. Yeah, take those out. So we got 2 million, 4 million, 1 million, 1 million. Yeah, these numbers I can manage with. I just have to do them one by one. So it'll take minutes, but I think we can do this. Right, so the next step is... So that, assuming that that the beacon in question is adjacent to this disk, and we're trying all disks, we want to now go through all the disks. No, wait. We want, for each of these candidates, we want to go through all the disks. And if it's ever in one of those disks, which is an easy check, it's an arithmetic check, it doesn't require any time, then we rule it out and move on to the next candidate. And if we come across one which is not in any of these disks, then that's the answer. It'll take a long time though. I'll need some print statements just to be clear on where we are in the algorithm at any given time. So put X, Y, R, so we know which disk we're on. Alright, so for this set of candidates, we go... It doesn't even need to be a set. Don't need to deal with the overhead of a set. Okay, so... for canned in candidates, actually we don't need a list of candidates, so we don't need to store this in memory. We can just at this point here deal with all the other disks. So alright, so we do for dx, dy, dr in disks, and it doesn't matter if we include the first one again because that's fine. if the absolute value of px minus dx plus absolute value of py minus dy, in other words, the distance from our candidate to this disk's center is less than or equal to this disk's radius, that means this beacon cannot possibly exist. So we break out of this for loop. So if we get through this for loop completely without breaking out, then we win the game. Beacon it's px py. All right, this. I hope this will actually run in a reasonable amount of time, but this is gonna. Okay, we're actually getting through disks. Oh. Okay, first of all. Alright, there's definitely a problem here because we're finding multiple beacons. We shouldn't be. The other issue is there's no candidates. What? What's going on here? Oh, because we're not storing them, so take that out. We're finding a beacon for every disk. That shouldn't be happening. So we're saying that we've taken this pxpy, which is on the boundary, so it's outside this disk, but it's also within the square. So for example, we're saying this one for 1, 6 and so on is within the square. Yes, it is, but we're also claiming it's outside every disk. Well, that's easy to check, isn't it? But that's what this should be doing. So px minus dx, dy minus dy. So we're claiming this is beacon. We can manually check this, so have I used the else correctly? If I break here, that means it won't hit this else, right? That's how for else works. Let me check this. Break statement executed in the first suite terminates the loop without executing the else clause suite. So it will only go to else if it never broke. So for some reason we're not breaking. Could be. Let me check these numbers are correct. 4 million. Sure. Okay, we know we can do this in a reasonable amount of time, so time is not too much of an issue. We're just finding lots of beacons. Let me make sure I've understood the question. I mean, these don't need to bracket this, do I? It's less than or equal to dr. Is it less than or? Hang on. Less than or equal to dr. Yeah, that's correct. Less than or equal to. Alright, let's take one of these beacons and figure out what's going wrong here. So, beacon, I'm going to say bx, by equals this. Or disk in for x, y, r in disks print. So we want the radius of the disk, and we want absolute value of bx minus x plus absolute value of by minus y. So the how far this is from the center. I'll just compare these by eye and see if stop. Don't do any of this stuff. So we're claiming this is a beacon. So we've got on the left is the radius of the disk, and on the right is this beacon's distance. It should always be large. The right should always be larger. Which does seem to be the case. 29575. Yeah. It is. So, does that mean this is a beacon? What else could we use to identify this as being confused? So by all accounts, this should be a this is a possible location for a beacon. What else do we have to narrow them down? It's not detected by any sensor, but the distress beacon must have X and Y coordinates each no lower than 0 and no larger than 4 million. So yeah, all these values are within 0 to 4 million. The only other thing I can think of is, are we filling in the disks correctly? Disks.append SXSY radius. So it's sensor X, sensor Y, and the radius is the distance of the beacon. The beacon they're detecting. So everything within this radius can't be a beacon. It's correct, isn't it? Let's try one of the other beacons then. Maybe this is the beacon and all the other ones are wrong. So that was one. Here's another one. How many do we find altogether? Loads. It doesn't make sense. Alright, so the other one we found is this one. Alright, so we've got interesting. So this is on the edge of the first disk again. So as before, so it's on the edge of this disk too. but as before, all the numbers on the right are larger. They should be. Yeah. So, I found 2 possible locations of beacons, and as far as I can tell, they are correctly outside all of the disks. So either my calculations are wrong, or there's a further hint that they've given us in the question to narrow this down, which I haven't used. It does say only possible position for the distress beacon. Oh. Am I... Oh. Let's see. It's just bad practice. I shouldn't have put discs at the end here. I should have put it here. The reason is... Oh wow, that was subtle. I have this here, which is continuing to the next loop, so it's bypassing the adding of the disc to the list. So I'm missing discs here. So that's why my result was weak, because it wasn't using enough discs to narrow it down. Yeah, but that was stupid on my part. I should have kept the discs with the relevant disc calculations. I don't know why I put it at the end there, because it was getting bypassed. All right. Let's try again. So we should only have one and only one beacon appear. Okay, we got one. Please no more. And actually the last thing we should be doing is print just print the result, which is we want to do multiply x by 4 million plus py. Yeah. And that's in the wrong place. Oh no, we do. Okay, it's the same beacon, but it's on the edge of 3 different disks, which is expected, because it has to be surrounded by disks on all sides, so it can't just be 2. It has to be at least 3, possibly 4 if some of them are on the corners, but it looks like it's 3. All right. Let's just get that. Oops. Get rid of that. Let's just get the tuning frequency. Alright, this was a very good problem. This really made me think. And it looks like it pretty much took me the longest out of any of the problems, but not by much. There we go. Oh, it's a nice big integer as well, just to screw with the C++ coders. Alright, so I think a lot of these problems have really benefited Python, and in some cases JavaScript too, but mainly Python programmers. Yes! Alright, that was good, and that was actually maybe one of my favorite problems so far. That was really smart. Because you have to, like, if they didn't tell you there's a unique beacon, you'd be kind of stuck. Maybe there'll be another way of doing it, but the fact that there's only one is a clue. That means that beacon has to be surrounded on all sides by disks. Otherwise, there would be two or more possible spots for the beacon. So that was a very subtle hint that I expect a lot of people might miss at first. Let's have a look at my ranking. What? I actually got a high rank for that? It took me ages, but apparently people found it really hard. Okay. That's my best rank so far. Oh, that's part 2. But it's still actually my highest rank so far for part 2. Part 2 is the more interesting one. Okay, part 1, I'm surprised I got such a high rank for that, because I could have coded that way faster. I would imagine a lot of people did. Yeah, no, I'm trying to think. I mean, there are actually textbook algorithms for doing stuff like this, but they're not easy to implement, so I wouldn't expect anyone to be able to do it for this particular competition. So yeah, it's all based on the hints they give you to take shortcuts. Yeah, that was very good. This problem, yesterday's problem was good. Yeah, these last 3 have been very good actually. So this one was the pathfinding one. No, this was the ordering one. That was interesting. This one was the sand falling, which is quite cool. 12 was the mountain climbing, right? Yeah. Yeah, these last 4 were really good problems and quite smart, and they used a bit of textbook knowledge and a bit of common sense as well. 11 was the monkeys one. Yeah, it was alright. Oh, it did use a number theory knowledge, so that was actually quite clever too. Alright. Okay. That's good. They're getting harder, clearly. So we're only about halfway through the advent. But yeah, it was also not something that a faster processor could deal with, because a million times a million is already beyond capabilities of any computer, pretty much. So it'd be a million. Yeah, it would be a million by a million. If you're counting up all the cells of each of these disks and crossing them out one by one. And I'm sure some people tried to do that. even for part 1. Alright. Alright, I guess I'll be back tomorrow. Same time, same place. So see you DAJ and Koo and Bad for Beans. Enjoy your lunch. Oh yeah, lunch. I didn't have breakfast long ago, but so I'm not as hungry as usual, but I will enjoy my lunch. Alright, thanks. See you tomorrow.